So, last class when I was saying that why it is important to color code the up, down, and quarks with something like red, green, and blue. So one of the primary reason was in order to continue with the quantum mechanical conservation laws. We do observe that there are additional quantum numbers required, and they are actually given in terms of the so-called colors called red, green, and blue. I also said that these green will actually have a complementary color which is G bar. I'm going to discuss that today. Blue will have B bar and red will have R bar. Okay, so these are the complementary colors. In nature, whatever exists more or less tries to exist in the form which is more or less neutral, so that's white. So that's where we actually stopped. Okay, and from there we can actually continue. So if you basically try to combine any of these two colors, you are going to get a third color, okay, which will be basically considered as a uh, complementary color. Okay, so combination of any two primary colors, okay, produce different secondary colors, right? So the secondary color, it means that if it can mix with the primary color, it will again give back a color which is white. Okay, so it is going to give you white back. Okay, so it's going to give you a neutral nature. So that is what is basically a secondary color is all about. Okay, so that means that we can say that these secondary colors, okay, are complementary to the primary colors. Okay, so these are the important points, and I think we can just take one example, and one of the example might be magenta. Okay, and I'm not very good with colors, but I'm sure some of you can really differentiate colors. Okay, different versions of red, different versions of pink. I'm really weak in that. Okay, for me red to red hi hota hai. But then these fine differences makes the main part of these color combinations that we usually talk about. So red plus blue will basically give you magenta, and this is basically complementary green. Okay, so that's why we basically call them as G bar. Okay, so we have got R plus B, and that is G bar. Okay, so what happens usually is that if we actually mix this, okay, so if we mix magenta with magenta, let me write it down, mixed with green. Okay, so what are the two colors we already had is red and blue, and then if we mix it with green, okay, we will get white. So that is why like this is more or less complementary. Okay, so in general if we just write it down here, we are just going to get it as R plus B plus green, okay, is equal to the white color. Okay, so white in general we have denoted it as P, so let me not change the notation, I'll just denote it as P. Okay, but this red plus green, which is red plus blue, which is combining with green to give you white, can be written as G bar. Okay, so if you look into this diagram, if this is G, this is G bar, which is red and blue. So in case I'm going to I'm asking you a question on drawing the Venn diagram for this primary colors, okay, along with the secondary colors, please may remember this logic. Okay, combined with the third color, it's basically going to give you white. Okay, so in general if we just talk about this colorless combination, okay, this is something which is being followed by nature. Okay, so that's why it is important. So some more points here. Okay, so for your exam purpose also, please remember that these questions, there will be descriptive questions, and basically you have to remember these things, these points, to actually incorporate it in your descriptive answers. Okay, colorless combinations are manifested in nature. This is quite obvious, right? Something which becomes more stable, and this colorless doesn't mean that we are talking about color in general. That's why we basically call it as so-called colors. Okay, these quantum numbers are so-called color. So proton will basically be nothing but red, green and blue. Okay, so it may be 2 up quark and 1 down quark, but then the color combination will be red, green and blue. Okay, on the other hand, if I talk about something like antiproton, although it's difficult, not yet detected, okay, but if we talk about antiproton and if we're talking about more or less in general antiparticles, this P bar would be nothing but R bar, G bar and B bar. Okay, so this is what is antiproton is all about. Okay, so in general, if you take up a meson or maybe a pion, okay, you're basically going to get different combinations. Okay, based on this, you're going to get this. Okay, so when we talk about quantum chromodynamics, why we really need quantum electrodynamics. Okay, so this is again important, or in general we can say when we talk about charge-charge interaction, does quantum chromodynamics helps us to explain something additional. Okay, so this is why it is important. So let's just talk about a bit about, I'm not going into the next unit, I'm just giving a brief to understand that what is the main reason we need quantum chromodynamics apart from quantum electrodynamics. So if we talk about quantum electrodynamics, okay, in general we can write it down as QED. It basically describes, okay, describes the interaction, okay, between electrically charged, so since it's electrodynamic, so it has to be some charge here, particles, or example, let's say electrons, okay, by, so how do they exactly interact, okay, by exchange of virtual particles or virtual photons, you can say, right? So this is what is quantum electrodynamics is all about. But what happens in general is if we have two electrons coming very close to each other, chances are they will repel. Okay? Quantum chromodynamics actually helps us to understand the conservation laws much better. Okay? So that's something which is important. So strong attraction, maybe we can say between two quarks, okay, cannot be typed, okay, by QED. So you've got two quarks which are charged. The chances are that they will basically repel. So quantum electrodynamics does not explain that, because as per quantum electrodynamics, two like charges will repel, right? So we need that quantum chromodynamics in the picture. Okay, since two positively sorry, positively charged quarks will experience repulsive Coulomb force, right? Repulsive. But if you look into the nature, this is not something which is there. It's not that they will always experience a repulsive nature force. So that's why we actually bring in the idea of strong force, right? So the strong force overcomes, okay, this repulsive force. Strong force will overcome this repulsive force. It's something which you already know, to bind the quarks in hadrons. So the quarks are bound in hadrons, and this is actually done by the repulsive force. Okay, and this so-called color charge also plays a role. So the so-called color charge, okay, of the quarks is responsible, okay, for the color field, okay, just as electrical charge is for the electromagnetic field. So whenever you have got any kind of electric charge, you know that there is a field around it, and on paper, at least theoretically, this field exists up to an infinite distance, right, up to infinity. But then a similar field we can also consider when we are talking about color. So if we are talking about something like up quark, okay, and let's say it's red, the color code is red, this will actually have its field up to a certain distance, okay. And if we have another blue coming in, up quark, another blue color coming in, and that will also have its own field, and both of these fields will actually overlap, and because of which they will actually start interacting. And this is what we exactly call as the quantum chromodynamics, the rule of quantum chromodynamics, okay. So these strong interactions are usually responsible because we do have something which we call as gluons. So let's just write down a few points about gluons, something which we already know, okay. So we have got the strong interaction between quarks, something which you already know. This is mediated by gluons. So the gluons is something which we already know, okay. And what are gluons? Something which we have already studied. These are nothing but gauge particles. So if you just look into the standard model, it's there. These are gauge particles, okay. So these gluons, we can say, are quanta of the color field, okay. So basically we can say the quanta of the color field. Just continue with the previous lines, okay. So continuation of the above discussion. Gluons are the quanta of the color field. So basically have the red field, the green field, the blue field extending, okay, and these gluons are actually the quanta of that. So that is the quantity, or that is the quantum particle which is actually there in that particular color field, or which is there because of the color field, okay. So the color field that bind the quark in hadron. So imagine this, uh, as soon as these quarks, let's say one red, one green and one blue, comes together, they are immediately in a state of binding. So they want to bind together, because combining them, okay, theoretically they were going to be neutral in nature, because they are going to be more or less white, and that means that this bound state will more or less be stable, okay. That binds the hadrons. So the best example that we know about these hadrons are nothing but the nucleons. So this is a eventual development in this, okay, we have to need to understand, okay. So what happens when the quarks comes into the picture? All three of them are coming in, and they are binding and forming a proton or a neutron, and then the proton and the neutron are coming in, and then they are also binding in to form the nucleus, right? So that is also actually having that similar field. So we can also include this, also the nucleons in the nucleus. So when you write it down in your exam, please make meaningful sentences so that it's clear. I hope I have not made it too complicated. The idea is quite simple, and that's the reason that I'm also writing it down. So the gluon is itself a colored particle. So if you just take up gluon, that is the field that is there, it's itself a colored particle, and it will be being depicted by, okay. So you take red and then you combine it with red complement, that will actually represent a gluon, okay. If you take a red and then let's combine it with the blue, okay, anti-blue, I'll just give that anti part, or you can take green and red bar, okay, or you can take red and green bar, okay, or you can take red and green bar, and so on. And you see that there are how many combinations possible, okay. So in general, if I just put it here, it will be red and red bar, blue, red and blue bar, green and red bar, red and green bar, and so on. So you can just keep on combining them, okay. And as soon as we have these color codes coming together, the interaction will start happening, and we have got the gluons there. That means the gluon plays a role at that particular range, okay. So if you just look into the combination of or the gluon combination, okay, in terms of the color codes, we can say that they are bicolored objects. So that is, okay, it is they are bicolored objects. So whatever we have studied till now, we can say that every quarks, okay, a quark rather, is characterized by two parameters. Okay, so two parameters, okay, or we can say, let me write down properties rather than parameters. By two properties, okay, and this is something which many of you could not answer in your exam, in your quiz. What is flavor? So basically, when we have quark, okay, quark is the entity under which we have got 6 flavor. Quark is the title under which we have got 6 flavor. Quark is the head under which we have got 6 flavor. And if you consider something like up, down, jump, strange, top, bottom, all are these are flavor. Okay, so in general, every quark is characterized by flavors. Okay, so you can have an example like up, down, strange, jump. Okay, I'm just giving you an example, not the list. And second one is color. So every quark is characterized by color. So we have got R, G, and blue. Okay, so if we just look into that table, there are 12 quarks. Okay, and 12 corresponding antiquarks. Corresponding antiquarks. So just look into this slide. A lot of information is being provided in this slide. Okay, and then I think you can understand this. Okay. So what we are discussing here is nothing but quantum electrodynamics. What is the challenge that it is providing? That when we have two charges of similar nature coming close, they are basically going to repel. But we have seen that the repulsive Coulomb force is overcome by the strong nuclear force. And how can we explain theoretically the strong nuclear force? The strong nuclear force can be explained theoretically based on the color code. So just as a charge has got an electric field around it, similarly, a quark with, let's say, a color code like blue, green, or red, okay, the quantum number, it will also have certain field. And if two quarks are coming and both of them are very close to each other, they are going to have that gluon getting involved there. Okay, so in general we have it here. Okay, so I think this got misplaced here for the R bar. Okay, so if you consider something like gluon, these are virtual particles just like photons, and they are more or less bicolored object if we go as per the definition of quantum chromodynamics. Okay, every quark is characterized by two properties, and it has basically got something which we call as flavor, which is up, down, strange, germ, and then we have got something which we call as color, which is red, green, blue. So there are 12 quarks and 12 corresponding antiquarks. Okay, so we will stop here.